Hello, Math 1224. This is Dr. P with Lesson Launch 401, the Bestiary of Calculus. What you're looking at here is a copy of the integral table from Hughes Hallett's calculus textbook. This is the table that I'm going to give you when we take our first exam in just a few lessons. So what you're looking at is a list of about 31 different types of integrals for which we know how to compute the antiderivatives exactly, analytically. Now you'll notice that there's a huge variety here, and I want to mention that this is not by any means a complete list of integrals that we can compute exactly. It's only a list of about 31 classes of integrals that come up fairly often in the sciences and engineering for which it is useful to know antiderivatives. Now remember, if I were to write down some random function composed of polynomials and exponentials and logarithms and trig functions and inverse trig functions and just went to town, there would be a good chance that the function I write down cannot be integrated analytically. It just wouldn't be possible. That there would be an antiderivative. It wouldn't be anything that we would know how to write down or come up with. But these are 31 classes of integrals which we actually do know how to compute analytically, and a lot of the ones on this list can be come up with just using techniques like the ones we've developed in class: substitution, integration by parts, and techniques we're going to talk about in the next section like partial fractions and trigonometric substitution. So anyway, the purpose of this video is to talk a little bit about how to use the table correctly, because there are going to be some integrals I'm going to throw at you that aren't exactly in the list but can be modified to produce integrals that are in the list. So for example, suppose I gave you the integral. I'm just going to move over here. Suppose I gave you the integral of 1 over 4x squared plus 1 dx. And I asked you to integrate that. Now, do we see anything in the table that looks like 1 over 4x squared plus 1 dx? Just going to look back here for a minute. We're going to scan the table. I'm just going to go through scan, scan, scan. I don't see anything here. Certainly nothing there. Nothing here that looks really good. Everything there involves natural log or an exponential or a sine or cosine. These all involve trig functions. But here I see some things that look promising. So let's just take another look. 1 over 4x squared plus 1. Now the problem with this table here is I don't see anything where the coefficient of x squared is something other than 1. But I could probably modify this so that it does have a coefficient of 1 on the x squared term. So let's see how to do that. There's a couple of techniques you can use here, both of which can be very helpful. So one of the techniques is, let's just take that integrand there, take the denominator, and factor out of 4. Now I know what you're thinking. I'm not sure I can factor out of 4. I don't see a factor of 4 in the constant term there. But what if I just went ahead and factored out of 4 anyway? I can do it. It's just not going to look quite as pretty. I'm going to have x squared plus 1/4 there now. Now, does that look anything like what we have in this table here? And it's starting to look a little bit like number 24 here. The only issue is that I have a factor of 4. So I'm going to take care of that by moving it outside of the integral. I can rethink this as 1/4 times 1 over x squared plus 1/4 dx, and then move that factor of 1/4 outside the integral entirely. Make sure I put equal signs here because all these are equal to each other. So now I've got 1/4 times the integral of 1 over x squared plus 1/4 dx. Now, the thing to keep in mind about using the table is if you want to use an entry in the table, you need to make that integrand conform exactly to what you see here. And I'm almost there, but I need to make sure that I've put this in the form 1 over x squared plus a squared, where a is a constant. And I'm almost there, but I just need to rewrite this as 1/4 times the integral 1 over x squared plus 1/2 quantity squared dx. And then I come back over to the table. Actually, you know, I just realized that this has got to be kind of annoying, jumping back and forth between my work and the table. So one thing I discovered I can do with explain everything, I'm going to come back to the table one more time. But I think if I ask politely, I can drag a rectangle here, create a copy of this that can then be moved over. Let me see if that'll work. See if I can grab this, move it over. There we go. Hey, how about that? Now we don't have to jump around quite so much. Okay, so anyway, I'm going to use entry number 24. Oops. Entry number 24 in the table. And when you use the table, I would like for you to state which entry you're using, just so that we were on the same page about what it is you're doing. So I'm using 24, and I'm going to write that this is equal to 1/4 times 1 over A is 1/2, 1 over 1/2 times the arctan of x over 1/2 plus c. Plus c. And then simplify that to get 1/4 times 2 arctan of 2x, because dividing by half is the same as multiplying by 2, plus c. And then there's no reason I have to leave that factor of 1/4 out there. I can just rewrite that as 1/2 arctan of 2x. And then this is a little bit sloppy. Really, I should write c over 4. But since all we're talking about here is an arbitrary constant and we don't know what it is, I'm just going to rewrite that as c, even though that's awful notation. In fact, I don't feel like encouraging that. I think I'd rather just write something else like a k there. So I'm not saying that c over 4 equals c. Anyway, so that, I believe, is my antiderivative. I could take the derivative and check that the derivative of that is what I started out with, 1 over 4x squared plus 1, but I think I'm going to leave that for you to do. Now I want to demonstrate very quickly one more technique that we can use to get the original integral into a form where we can use the table on it. So I'm just going to start here one more time and use a different color. So let's start again with 1 over 4x squared plus 1 dx. Okay, now again, the fundamental issue here is I want to have a coefficient of 1 on that x squared term. That's still the issue here. But another way I can get there is I can say, look at this 4x squared here. I know that that is 2x quantity squared. So I can use the u substitution, let u equal 2x, and then du equal to 2 dx. And I don't see an extra factor of 2 hanging around, so I'm just going to go ahead and rewrite dx as 1/2 du. So I'm going to say this is equal to the integral of 1 over u squared, where u is 2x, plus 1, and then times 1/2 du. And then let's just go ahead and chase this down. I can actually recognize that this integral here as the arctangent of u. But if I didn't know that, the table could tell me that. That's what entry number 24 is telling us. So in this case, I would be using a equals 1, because this is really the same as 1 squared. And then I can say that this is equal to, by number 24, this is equal to 1/2, just moving that out, times the integral of 1 over u squared plus 1 squared du, and that is 1/2 times 1 over a, which is 1, arctan of u over 1 plus c, which comes out to 1/2 times, and then that's just 1, arctan. And then what was u? Well, u was, it was just 2x. So arctan of 2x plus c, which I think if I zoom out, I'll see that that is the same thing I got earlier. Yeah, would you look at that? So I have 1/2 arctan 2x plus k here, 1/2 arctan 2x plus c here, just the name of the constant was different. So anyway, that's a basic demonstration of how to use the table. In the next video, I'm going to show you how to use the table on a more challenging problem. That's it for now.